So coming down into exam 1. So here's some of the materials that I put out there to help. So for some people, you've had this recently, so it's just kind of brushing up on some of this intro stuff. For other people, it's been a while. So things that I did, and I'll blow this up so you can see a little bigger. First one, exam 1 review, that's that handout that I gave you. So that's the handout that was with the balancing equations and unit conversions. That's just to help you organize information. So to ask yourself questions and fill things out as you organize it. So everything that is this, these are YouTube videos, and they're actually our lecture. So what I did is I recorded chapter 1 when we did classifications in matter the first night. Then the second one is going from unit conversions through significant figures. Then I did the out of class because we missed class Monday night. I did this out of class lecture, and that actually finishes through balancing equations in the end of chapter 1. And then I still have students who are like, there's still some things I feel a little bit like, yeah, I don't know if I'm there 100%. So I did another practice video, and this one's only like 20 minutes long. It's 10 PowerPoints, and so I actually made up new PowerPoints, like just a little short 10 PowerPoint slide that you can open this. You could print it if you want to like handwrite and like fill things out as you go. But this is an out of class practice. So all that happens when you open these is it opens a YouTube video. Don't start. Okay, so it didn't start. It just opens a YouTube video, and then, like, so this one, how long? So this one was 33 minutes. This one I went through and just did things like practicing, like identification of the classifications of matter. Then I went on and fill them out, talking as I go. I also went through and did the more unit conversions, just going back over the process, hopefully lab tonight. One lab today will really kind of like cement unit conversions for you, helping you see how to set them up to flow through. But I went through and just did some extra ones. When we got through, then I went through significant figures again, okay, just to remind you, okay, how do you find them? I made up some new numbers, so we went through those practice ones. So if you're still even a little leery about things like how to round with multiplication and division in significant figures, what happens with addition and subtraction. So I went through some extra examples. They're not the same examples in the regular PowerPoint. I changed some of the numbers just to give you a little more additional. And then at the end, we did exponents. I did an example of percents. I did an example with accuracy and precision, like how do you recognize something, numbers that are considered accurate versus numbers that are precise, sort of to link those ones together. And then towards the end, I did a density, another density example, and finished it up with more balancing equations. Okay, so these are really kind of like the active math or active practicing, problem solving kind of stuff in chapter 1 that I just find that people sometimes struggle with. And it really just depends on you. Depends on how familiar this is or how new it is. So if it's really new, this practicing, especially this first chapter material, is really going to help you with future chapters. If you don't get unit conversions down in this chapter, it's going to hurt you in the second exam, the third exam, the fourth exam, because we use it continually the entire semester. Not getting the balancing equations down, you're going to see that that's going to end up coming back. We talk about it again in chapters 4 and chapter 5. So we're going to come back to these. It's not something that I'm going to talk about this today, and we're never going to talk about it again. So that's why I went back and did like a little practice. Okay, so if you're still struggling with any of those, the other thing that I will tell you is I've posted now, I finally got our times figured out. See if I can make that shrink. There. I got our times figured out for tutoring. So Gus Griffith, he is our student tutor. He's taken general chemistry 1 and 2. He's taken organic 1. He's in second semester of organic chemistry. So he's had a lot of math. He's had a lot of chemistry. He's taken physics. And so for him, the level of this math, of the math and the chemistry in this class, not a problem. He was my tutor for last semester. I have actually worked out more like worksheets and things like practice problems and given to him, so he actually has things to work out with you so that you don't just have to walk in and go, I don't know anything. You can like go in and tell him, I need to work on unit conversions. I need to go over significant figures. I need some help with balancing equations. He has more problems to help you with. He is in the still. So the still is that small computer lab that's upstairs, 7D213. He's here on Tuesday and Thursday afternoons, like late. So that's a big help for you guys if you can't come because you work during the day. He's here from 4 to 6 on Tuesdays and Thursdays, 9 to 12 Tuesdays and Thursdays, 4 to 6. I am still in that same room from 3:30 to 5:30 on Mondays before we have lecture. I'm in there. I'm also in there on Thursdays after I get done my day class from 11 to 1. Miss Williams, who is the other chemistry instructor, she is in the still on Tuesdays in the mornings and then on Fridays too. So any of those times, you are more than welcome to take any kind of questions. Could be questions in your homework, questions in My Labs Plus. It could be questions that are related to like just things that are talked about in lecture. You can take any of those to any of the three of us. So it kind of really gives you about 16 to 18 hours a week that there's tutors, and it doesn't cost anything. All you have to do is just sign in. Okay, so when you go in, they'll have you sign in. We just try to keep a record of how many students use that room and if making sure that it's useful for students as well. Okay, so I do have that posted. That's on at the very top in the Chem 130. And then like I said, I posted this last marked up PowerPoint for chapter 1 is actually the PowerPoint after I completely finished it. So it now has all of the notations that I made in all of the lectures through chapter 1 all the way through balancing equations. So those are just things that maybe help to like just give you more. Like I said, some people are audio, some people listening to things, it really helps. Some people like they want to see it written, like watching you write out a math problem, then suddenly it's like, oh, I see that. Whereas somebody talking about it, it does nothing for you. Some people reading it's fine. Some people, they have to do it themselves. So printing out those PowerPoints, if you're a mechanical learner, printing out the PowerPoints and actively trying to write out examples as we go through them, that's really going to help to make it more cemented for you. Okay? So is there any questions? Was there any like major difficulties that you ran into? Hopefully the My Labs Plus assignments as well, there's a significant figure dynamic study module, a unit conversion dynamic study module, and understanding matter dynamic study module. So hopefully those ones have also kind of helped to reinforce. Make sure you should be about finished all of those things for chapter 1. So what I wanted to cover tonight, what I wanted to talk about tonight is looking at chapter 2. So chapter 2 is putting together information about atoms. So we've kind of talked about elements, talked about compounds, talked about some of the basic material and matter. But chapter 2 now starts to look at the individual particles. Not this one. These subatomic particles. So though we said that you've got elements, so all the periodic table, the 118 elements that are known, when you look at an element, all of the particles that make up an element are made of atoms that are similar. Well, they found that there's actually parts that make up atoms. There's actually more than these, but for us, we're just going to cover the 3 general as a 3 basic, no quarks and none of the neutrinos or any of that. We're going to talk about the basic 3 that are protons, neutrons, and electrons. They differ in location, they differ in size, they differ in charge. So those are sort of the 3 things that we're going to characterize them by. So if you just take an atom, and if we just say, okay, this is an atom. Here's our general circular structure. We're going to call that the atom. The smallest unit of matter. If we're looking at protons, neutrons, and electrons, you find that protons and neutrons, they are found in this really small space, typically more centrally located. They call that the nucleus. Very similar like the nucleus of a cell. Always kind of that central circle, central space. The nucleus contains protons and neutrons. All of the space outside of the nucleus is where you find electrons. So this is one way that they differ. Protons and neutrons in the very center, sort of in this tight little core. Second way that they differ is they differ in terms of their size. So when they tried to start measuring, well, how big are protons, neutrons, and electrons? They're super crazy small. They're that like 1 × 10 to the minus 20th grams, really, really small in size. So they're like, that's not very useful, okay? So if we just look at how big they are compared to each other, protons and neutrons are larger than electrons. So they said, well, if we say that protons and neutrons just have a mass of equal to 1, and this mass, they call it an atomic mass unit. It's really a generic mass number. We're just going to say if these ones are 1, electrons are 1/2000th that size. So electrons are teeny tiny. So you know there's not even 2,000 elements. So we can't even have like 2,000 electrons in an atom. So relatively, they say that electrons have negligible mass. They do have mass, because remember that makes them part of matter. They have to have mass and take up space. So they are part of matter, but their mass is so small, it doesn't end up affecting the mass of the atom as a whole. So size-wise, protons and neutrons are much bigger than electrons. They're also different by charge. Each one has a different charge, and you'll oftentimes see them written indicating what their charge is. Protons are positively charged, and you'll often see them written P with the little plus, indicating that charge. Electrons, you see them written as an E with a little negative. So they have a negative charge. So protons are the positive charge. Electrons have that negative charge. And neutrons are neutral. Okay, so that's kind of how part of their names came up from this. You'll sometimes see neutrons written with an N with a little 0, which is sort of like saying that they're neutral or that there's no charge connected to them. So they differ by location, they differ by size, and they're different by charge. But now if you look at the atom, you would say, where is all of the mass of the atom? Where's it found? It's in the nucleus, right? So notice that because protons and neutrons are the ones that have relative mass, you would say that really all of the mass of the atom is in the nucleus. And electrons, they don't just sit in their little spots. Electrons, being these teeny tiny little particles, are actually in this constant motion around the nucleus in all that space. So they're constantly moving, constantly moving. But what do you know about positive and negative? They attract each other, okay? So that the nucleus has got protons and neutrons. Neutrons are neutral, so they're not going to have an effect on a charge. But protons are positive, and those little negative electrons, they're moving, but they're still kind of attracted to those positive protons in the nucleus. That's why they stay in their position. So kind of think of like the moon, how it orbits the Earth. Very similar, that fast movement. They don't go flying off, they kind of stay in that space, and it's all because of their charge. Now what's great is you can actually, and there's like kind of like the summary of what I just said. What's great is you don't actually have to memorize how many protons, neutrons, and electrons there are in any given element. All you have to do is know how to use a periodic table, because it's all in here, okay? So things when you look at the periodic table, let's look at lithium, for example. So lithium is Li. When you look at the periodic table, you have the symbol Li for lithium. The number above is what? 3. The number below is 6.941. So the number above is called the atomic number. The atomic number is really the identity of the element. The atomic number tells you the number of protons. And all elements that have atomic number 3, every single atom with atomic number 3 is lithium. And it behaves like lithium. It has characteristics of lithium. So it doesn't matter if you have a pound of lithium or if you have a few grains of lithium, just a few little small particles. If its atomic number is 3, it has 3 protons, and that is a lithium element. But now, in a neutral atom, protons, being positively charged, are going to be equal to what? Equal to electrons, because electrons are negatively charged. So if the atom is neutral, like if you were just looking at the element lithium, the number of protons and the number of electrons are the same. So in a neutral atom, not a charged ion, so you know how like sodium exists as Na+? That one doesn't work that way, okay? But if you were just talking about lithium, number of protons and the number of electrons are the same. So atomic number is the number of protons. It's also the number of electrons in a neutral atom. So that means, like, now that you know what symbols are, I could give you any of those 30 symbols. So like with Hg. If I ask you Hg, how many protons does it have? It's got 80. How many electrons does it have? 80. And Hg is what? Mercury. That is one of the ones to learn. The name and the symbol. So I'll give you the name Mercury. You can just look at the periodic table. It's that atomic number. Number of protons, also the number of electrons. So notice in here, so they kind of show you, here is the atom. So see the 3 red, those are the protons, 3. See the 3 little itty bitty blue specks? Those are the electrons. Remember, they're 2,000 times smaller. So that's why they even show them being really small in comparison. But now, what about neutrons? How many do you see? 4. Okay, so see the gray? If you count, see them in the nucleus. So there are 4. The way to figure out that is looking at what's known as the atomic mass. So the atomic mass, I told you all of the mass is in the nucleus. So the atomic mass is because of the number of protons and neutrons. So the easiest way to figure out the number of neutrons is to take the atomic mass and subtract the atomic number. Because atomic mass is protons and neutrons. So if you subtract the number of protons, that'll tell you the number of neutrons. So to figure out numbers of neutrons, take the atomic mass. For us, just round it to a whole number. So we're going to take 6.941 and we'll just round it to, round it to 7. Subtract the atomic number from the atomic mass. That's going to tell you numbers of neutrons. So go back to Mercury, go back to Hg. It has 80 protons, 80 electrons. How many neutrons does it have? 121. Okay, so you see how it is. So Hg is 200.6. Round up to 201. Okay, 201 minus 80, 121 neutrons. So you can do that for any single element. That's all you have to remember to do. Atomic number at the top is numbers of protons and tells you numbers of electrons. Atomic mass rounded minus atomic number tells you numbers of neutrons. So the next question people have is like, well, let's do a couple just to practice. So Ag, so what does this mean? What's this symbol? What's the name? This is silver. Okay, how many protons? Okay, so you find Ag, 47. How many electrons? 47. How many neutrons? So 108 minus 47. Just take the bottom number, round it to a whole number, subtract the top number. Figure out numbers of neutrons. Na, what's Na? Sodium, not sulfur. Sodium, how many protons? 11. How many electrons? 11. How many neutrons? Yeah. So we just took 22.99 round to 23, subtract 11, gives you 12. Interesting, the small elements, protons, neutrons, and electrons are usually really close. Like lithium, we said there's 3 protons and electrons and 4 neutrons. Here, sodium, 11 protons and electrons, 12 neutrons. Numbers are really close. The bigger you get, TH, I will tell you, that's not one of yours you have to know. It is thorium. Thor. Find it. It is all the way down on the very last column, and so it is 90 protons. How many electrons? 90. And then how do you figure out, so neutron number? 232 minus 90 is 142. That's a lot of neutrons compared to protons and electrons. So when you start getting lots of neutrons, what do you think starts happening to that nucleus? So that nucleus gets like tighter and tighter. The bigger the atom, the bigger the element, the larger the protons and electrons. But then you start getting more neutrons, even more than what you see protons. So that nucleus starts getting really tight. Some elements are not stable with large numbers of neutrons. And that's where radioactivity comes into play. So that's really what this whole entire chapter is looking at how atoms that may have larger than normal numbers of neutrons become more stable by rearranging their subatomic particles. So just as one side, here's like one way that we can write an element if we're talking about an element with a specific atomic mass. And do you notice this is weird? So look at carbon on your periodic table. What's above? 6. And below? 12.01. So when you look at it this way, do you notice? I didn't make these rules. Like, this is how they did it before. I just don't want it to throw you, which is why I want to show you this symbolic way that they like to write elements. So notice this carbon, the 12's above. So if you have it written and it's above and below, just remember the bigger number is always the atomic mass. Okay? The larger number is always the atomic mass. The smaller number is always the atomic number. But in nature, there are some atoms of carbon, like this. This one has how many protons? 6. That means it's got 6 electrons and 6 neutrons, all exactly equal. And most of your carbon atoms are exactly that. But in nature, there are very small amounts of carbon atoms that have more than the normal number of neutrons. So there is actually carbon atoms that are this. So how many protons in this one? 6. How many electrons? 6. And those are the same. Like, that's because I told you protons, that's what defines the element. If it has 6 protons, it's carbon. If it doesn't have 6 protons, it's not carbon. That is like the definition. So that number 6 is what defines the element. But this one has how many neutrons? 7. The only way they differ is numbers of neutrons. And it's because you can like pack an extra neutron in that nucleus. They're still going to behave like carbon. In fact, there's another one. There's one that looks like this. This one has an even higher number of neutrons. Still, 6 protons, 6 electrons. This one has 8 neutrons. All three of these are found in nature, but 99.9% of the time, it's this. So they say that this is the most common form of carbon, and you notice that the atomic mass on the periodic table for carbon is 12.01. Very, very close to that common form. But it's 12.01 because there's very, very small amounts of the other ones. And so the numbers on the periodic table for mass are called the average mass. It is the average of all three of these. Not average like add them up, divide by 3, but average based on their relative abundance. So this one is like 0.06%, and this one is like 0.04%. Really, really small amounts of these other two. Most of it is going to be the one that has 12 as its atomic mass. So they would say that's sort of the most common form. But all three of these are carbon. They differ by mass. These are isotopes. They're all carbon. They all have 6 protons. They only differ by numbers of neutrons, so they differ by mass. No, hydrogen does because, well, no, hydrogen does not. But there are some isotope forms of carbon, of hydrogen that do. So proterium is with 1, deuterium has a neutron, and then tritium has another one. Mm-hmm. So this is the reason that your atomic masses on the periodic table are a decimal. But for us, if I asked you how many protons, neutrons, electrons in a carbon, you would just take the atomic mass and round it, subtract the atomic number, and that's the most common isotope form. Sometimes they'll write it this way as well. So if you saw carbon 12, that's the same thing as this. So it's just another way of talking about it. So you might see it. I don't use it this way all the time, but if you're going through and you're working on any of the chapter 2 stuff in MyLabs Plus, if you see that, that's what they're referring to. Is just remember that's telling you what the mass is of that specific isotope. So that's a single atom of carbon, and it has a mass of 12. Here's their example with calcium. So calcium can exist as calcium 40 or calcium 42. So notice that when you look at the symbolic notation for them, same atomic number, different atomic masses, and they differ just by different numbers of neutrons. So this is sort of like the key. If X is the symbol, the number above, just remember the bigger number is always the atomic mass. Okay? The smaller number is always the atomic number. And that way you won't get them mixed up if you're looking at a periodic table or if you see them written out in their weird isotope forms. Okay. So some of these isotopes, they're not stable, and so they want to actually become stable. In doing that, they break down. Doesn't happen with all, but some isotopes of elements, usually it's ones with more than normal numbers of neutrons. So the more neutrons you have, the more packed in it is in the nucleus. So it's usually those with more neutrons. They can be unstable. So the goal is to become stable. And to do that, they undergo what's called radioactive decay. So, if you think of something decaying, it's breaking down. So radioactive decay is an atom's way of trying to achieve stability by changing its internal structure. So it may change its proton-neutron numbers. It may actually push or shoot energy out, which creates nuclear radiation. Sometimes it's just energy. Sometimes it can actually be particles that get shot out as well. So this is really a new branch of chemistry because this wasn't really described until the 1900s. So you're only talking about something that's about 120 years old. So all this other stuff, they had like figured out protons, neutrons, electron numbers. So Henri Becquerel, he actually got a rock that contained uranium. So he had it in his lab. And so he was taking photos and stuff, and he went and developed this film, and it was like white, like somebody had taken and put it out in the sun. So he was like, must have had a bad batch of film. So he went and got more film, had it in the lab, took pictures of normal, went to develop it all white. He's like, something is like changing my photography film. Something is exposing my photography film. And so next time he's super careful, keeps it wrapped up, nobody's allowed anywhere near it. Same exact thing happens. So then he starts putting it in different places. Let's see if we can figure out exactly where this is coming from. And so he found when he put it next to this rock, his film would be exposed. It would be just white, as if somebody took it out and put it in the sun. So he was like, there's something coming out of this. And this was this discovery that there are substances in this uranium, it doesn't glow. It doesn't actually look any different, but it's constantly releasing this energy as it's going through this sort of goal to try and become more stable. So most isotopes are stable and they're not radioactive. So most, like when you're talking about like carbon-12, it doesn't break down. It's perfectly fine and stable. Most of the ones are ones that are big and have a lot of neutrons, okay? So ones that are 83, so when you're like looking along, so 83 is BI, that's bismuth. So from there are more common radioactive isotopes from that size up as you go along, and in there you can see like radon, if you've ever heard of radon gas, okay? So then you have radium, which is one that Marie Curie described. She named it that because it glowed. So she had radium, and she actually used it like a little night light beside her bed, which is not a good thing. She died of leukemia.
I was about to
Okay.
say
So
radiation,
then,
right?
yeah, you keep going along. So uranium, that is one that they use in the nuclear energy producing. So as you get into these larger and larger elements, it's more common for them to be radioactive. But there's some small isotopes, like hydrogen has an isotope. It's small, very small percent, but it's actually radioactive. Carbon-14. Carbon-14 is a radioactive isotope, okay? And that's carbon, which is found like everywhere and in all living things. But it's a very, very small amount, and it breaks down very, very slowly. So it's not something that's like glowing and releasing lots of energy like a uranium rock is. So how do these do this? So there's really three we're going to talk about. So when radioactive isotopes break down, they either undergo what's called alpha decay, beta decay, or gamma decay. So these are really the ones that we're going to talk about. There's two that are less common, which is why we're not really going to focus on them. Here's alpha. Alpha decay occurs when 2 protons and 2 neutrons get shot out of the nucleus. So you're talking about an isotope, so inside there's too many neutrons, and so to become stable, you're going to push a couple of them out. So if you lose 4 particles from the nucleus, what's going to happen to the mass? We said protons weigh 1, neutrons weigh 1. So if we lose 4, mass will go down by 4. So we're going to decrease atomic mass by 4. 2 protons get shot out of the nucleus. So what's going to happen to the atomic number? It's going to go down by 2. The atomic number goes down. Is the symbol going to stay the same? No, because remember we said atomic number defines what the element is. And so the symbol is going to change. It'll be a different element. So the element symbol and name changes. So the easiest way, the way I remember it, is I think of this, and I'll always put that in a chemical reaction. So starting with uranium. So uranium-238, that's the atomic mass of this isotope. Notice its atomic number is 92. So if you find uranium U, you see it's a 92. So if you look at theirs, so their number is 238 is its average mass. So I got the same, pretty close, but it's radioactive, even though that's the most common isotope. So 238 is the mass. Mass will drop by 4. So what's the new mass going to be? So this will become 234. Subtract the 4 in order to make the new atomic mass. What's the atomic number going to become? It'll become 90. So now you got to look on the periodic table and find element 90. What's its symbol? TH. So it actually becomes, it like converts to a different element. So it stops being uranium and it converts to thorium. It's a little more stable, although it's probably not done breaking down. So they like continue to do this until they become more and more stable. So CF is californium, so you wouldn't have to know that. It's not one of your ones to know. I think it's a great name. So californium 257, when it breaks down, it undergoes this alpha decay. So same thing happens. What happens to the mass? So it's 253. What happens to the atomic number? Goes down to 96. 96 is CM. That's curium. This decreases the number of particles in the nucleus, and that's going to help to bring this atom to a more stable level. So beta. When beta occurs, a neutron converts into a proton and an electron gets shot out. So in this one, a neutron becomes a proton. So a neutron has a mass of 1 and a proton has a mass of 1. So what happens to the overall mass? Stays the same. So the atomic mass, which is the top number, has no change. So that's why when I write it with this symbol, see the 0 at the top? So that means like it's not going to change. So 14 minus 0 is not going to change that number. The bottom one, a neutron becomes a proton. So what happens to the atomic number? It's going to go up by 1. Okay? So atomic number, the bottom number is going to increase by 1. And if your atomic number changes, does the element change? Yeah, because that's what defines it. So you'll have a different element name symbol. You always use the atomic number to figure it out. So here's how carbon-14 breaks down. Carbon-14 breaks down by beta decay. And so what happens to the mass? The 14 stays exactly the same. So what happens to the atomic number? It goes up to 7. And that is nitrogen. This, though, if you look at the periodic table, see the element nitrogen? Its atomic number 7. See that its atomic mass is 14.01. That's really stable. So that's going to make the more common isotope. That's the much more stable. That's got 7 protons, 7 neutrons, and 7 electrons. So we're now back into like having more of an even balance protons and neutrons in the nucleus. That's going to create more stability compared to what carbon-14 was, which had 2 extra neutrons compared to numbers of protons. Copper. Copper-66 breaks down. When copper-66 breaks down, what happens to the mass? So 66, the atomic number, 30. And that is zinc, Zn. And if you look, the atomic mass of zinc, the average mass is 65.39. Now we're at 66. So it's actually brought it closer to what the average is, helping to improve that stability. So with these, here's the big thing. If you can look at a reaction and you can see that and recognize, oh, that's the beta decay. If you see the helium nucleus, that's the alpha decay. So if I give you like an example, I will finish the reaction for you. I will say this reaction is an example of. So if you see the helium nucleus with the 4 and the 2, then you know that's alpha decay. If you see the electron with the 0 and the -1, that's beta decay. But just remember, they're breaking down because they're trying to create more stability in the nucleus of each atom, trying to make protons and neutron numbers more even. okay, rather than having a big difference between them. So we're not going to do positron because we don't use that. I mean, there's some, but it's not a huge thing. Gamma decay, though. So gamma decay is the third. Gamma decay is super easy because no particles, no change in mass, no change in atomic number, no change in symbol. So gamma decay is really the energy that is released when this rearrangement happens. You can have gamma decay happening with alpha. You can have gamma decay happening with beta. And you can have gamma decay happening just by itself. I think of this as the energy when those particles in the nucleus shift about. When they try to like position themselves more comfortably in the nucleus, that's when you get gamma decay. So they use this symbol. So the symbol, it looks kind of like a strange, it's almost like an 8, almost. It looks like that. I can't draw that very well. So my drawing, it looks kind of like that. But that's what it'll look like on your test, because I'll like copy that symbol. Put it on there, because I can't draw it right. Okay? So this is a lot of energy, but no change. So if I have plutonium-250 and it undergoes gamma decay, it's just this energy that's being released from this radioactive substance. It's still going to have a mass of 250. It'll still have an atomic number of 94. It is still going to be plutonium. Okay, so it's not going to change, but it's that energy that's represented. And that's a significant energy. This is energy that is stronger than X-rays. We're going to talk about like the strength of these three in comparison. So let's talk a little about, where are you? X-rays. So X-rays, and everybody's had an X-ray done, okay? Or you've seen like an X-ray machine. If you've been to the dentist, you've had X-rays done on your mouth. So these are high energy waves that are made by directing a beam of electrons. So those little electron particles, high energy, is shot at this metal. And one of the most common metals that's used is tungsten. So when electrons hit this tungsten, that causes energy waves to like bounce off. Those energy waves can pass through soft tissues. And so that's the benefit of it, because it'll pass through anything that's soft. So that would be like skin, that would be blood, that could be your subcutaneous tissues. But what stops it? Bone, okay? So solid, dense structures are going to stop it. So they found that this was really useful to do because you could take and put a structure, which is in somebody's hand, okay? If there is any kind of damage, and it wouldn't necessarily have to be like broken in half, bone piece sticking out, but they found, okay, if we actually focus the energy from that X-ray machine, so when they turn it on, a high beam of electricity hits tungsten, tungsten bounces that energy off and creates this X-ray. X-ray passes through the skin, passes through muscle, passes through all the soft tissues, but it's going to get stopped by bone. And so if you put a piece of film underneath, so those waves pass through everything, and it can pass through an area that's damaged because that area is going to have fluid collecting. So in an area where there may even be a very small crack, that will show up because the X-rays pass through. So they pass through any area that's not solid, and that allows them to actually see without actually having to do surgery. So prior to that, literally, if your bone was sticking out, they'd be like, yeah, your bone's broken. But before they had X-rays, they would be like, it's really swollen, so we'll just put you in a cast. We don't really know if it's broken. Like, they don't really know. And they didn't really know necessarily if they needed to do surgery to pin or put things back together. And so you would end up with, a lot of times people would end up with a leg that's shorter than the other because they didn't have the imaging. So remember, this is like 1900. They didn't have the imaging prior to. And so that was a really common problem with breaks, that they weren't identified, they weren't repaired, and so they ended up having long-term scarring, long-term sort of deformation in those bones. So now we actually have developed the film and the technology so that the amount of energy you're exposed to in an X-ray is about 1,000 times less than what you used to be exposed to. So back in the early 1940s, 1950s, like people would go get X-rays of their hands for fun. Yeah, it's just really neat. Look, you can actually see your bones. But they were actually exposing them to a lot of energy, a lot of this energy from that metal. And so they found that there are some negative side effects to that. So as they have developed film, like they developed photography film, and then it developed into digital. So now you can actually, with the digital film, you can actually look at layers. So rather than just getting a flat picture, you can actually have film where you're seeing layers of an X-ray and you're still being exposed to so much less energy than anything that you were 40 years ago. So why does this cause problems? So we're saying X-rays, the energy from an X-ray, gamma rays are higher. Alpha and beta are lower, but they're close. So they're very similar in characteristic. So any type of energy has the ability to do what is called ionize. Ionizing radiation means that that energy can cause damage to atoms in living cells. So what kind of damage? Well, it could cause damage that could lead to genetic changes. It could cause damage that could lead to disease production. It could cause damage that could cause that cell to die. So all of those types of things, like cancer, a disease could develop, and it's because that energy causes damage into living cells, and if they're not repaired, then that can end up causing long-term consequences. So if you, as a healthcare worker, are working around X-ray equipment, or if you are working around patients that have had any type of radiation therapy, that concern is true and logical, dependent on the form of radiation that was used and whether it's still in the person or if they were just externally exposed. So you wear things like a lab coat. You wear goggles. You may wear gloves. When dental techs take X-rays, where do they go? They don't stand right there. They step around the corner. Well, the reason they step around the corner is because that wall has a shield in it so that that energy doesn't pass, so that they're not going to get exposed every time they're taking a dental X-ray. And that's where the button is, and that makes sure that you actually go around that corner and hit the button instead of standing next to the patient. It's a bigger concern, like if I don't know if any of you are going to be vet techs, but can you like go, okay, doggy, lay right there and I'll be back? What happens if you do that? The dog is going to jump up and try to follow you, right? So with vet techs, they have to wear shielding. So they wear shielding to try and protect them because they actually have to stay with their patient. They don't have the option of like going around the corner and limiting their exposure, but they still take shielding precautions. They'll use a film badge. So if you take a lot of X-rays, you're going to wear a film badge. And a film badge, if you're exposed to ionizing radiation, that film badge will show it. So every month you take your film badge and you pass it in, and they develop it to see how much energy have you been exposed to this week or this month or in this work period. And so that way they can make sure if you're approaching what they consider high normal levels, then they can limit your exposure to make sure that you're not getting exposed to anything that could potentially cause damage. So blocking. Alpha, big particles, thing to remember with this, big particles don't go very far. Okay, so alpha is a helium nucleus. Alpha is, remember, 2 protons and 2 neutrons. So alpha is really like a big particle. And so it doesn't go very far. Alpha you can block with a piece of paper. So if you had a sample that was releasing alpha radiation, put a piece of paper over it, it's not going to hurt you. Okay, it would be able to be blocked. So that means if you're exposed, it would be the very superficial layers of your skin. So it is not going to pass all the way through. Beta, on the other hand, is this energy that's associated when you have a neutron converting to a proton, electron gets shot out. So there's a particle, but it's not very big. So compared to 2,000 times smaller. So it's pretty small. That means that it's going to go further. So beta decay can pass through the skin and into, so it goes down into soft tissues, okay? So this goes into soft tissues So if you want to block your exposure, then you use like a piece of plexiglass. So plexiglass, like you can think like of Carolina hurricanes, like those glass, all of the protection for the fans. It's usually about a 1/2 inch. That's the normal. So that will block. That will block beta decay. You can use a thick, not like regular aluminum foil, but you make that heavy duty aluminum foil. So heavy duty aluminum foil, that'll work too. So you could take and cover a sample that is a beta decay emitter, cover it with thick aluminum foil, and that's enough to block it. The gamma and X-rays, they go through soft tissues. X-rays get blocked by bone only. Otherwise, like through the area that's soft, it would pass all the way through and out the other side. So it doesn't get stopped by soft tissues at all. It only gets stopped by bone. Gamma doesn't get stopped by bone either. So gamma just passes straight through you. So this goes through the body. And as it passes through the body, it has the ability to cause ionizing damage within body cells. So that's the concern with exposure to gamma. So in blocking this, you use lead or you use concrete. So when do you use lead? Concrete's kind of hard to like move around, but you can move lead around. Lead is really dense and it's pretty heavy compared to its volume, high density. Lead can block gamma and X-rays. So when do you use lead? Have you ever had anything with lead you've had to put on? Yeah, so that's the shielding. So like I said with the vet techs, they actually put on like an entire lead little vest piece, flips up over their shoulders, comes all the way down to here. Even if you're getting like an X-ray of your hand, they will still take and put a shield over your abdomen and your pelvis. What are they trying to protect? Which ones? The what? The reproductive organs, because that's where the eggs and the sperm are, and they are less likely to be repaired. So ionizing damage to them can end up leading to an inherited disease. So that could end up leading to offspring that would end up having damage to those cells, could end up causing problems that way. So you could end up with birth defects, or you could end up with miscarriage, all kinds of problems like that, which is why anytime you have an X-ray, even if it's just on your teeth, they always ask you, well, not you, but they always ask women, is there any possibility you could be pregnant? Okay, because if there's any possibility, they're really going to limit. There's a question then, do you really need this X-ray? Because even though it's very, very low energy now compared to what it was 40 years ago, they're still going to try and limit it. So lead shielding, if it is something that is used on a continuous basis, like what happens in nuclear power plants, they use concrete. So that way they actually enclose any type of high gamma emitters with concrete about 3 feet thick, and that's enough to block that energy. So those are the differences between alpha, beta, and gamma in terms of like its ability to penetrate and then also your ability to block it. So now if we go and we use these, so these are used in medicine. We use alpha, we use beta, we use gamma. So it really depends on the usage. Or there's another example. I want to skip these ones for now, so we won't do the math in these. But I want to talk about, you don't have to worry about the half-life things, the use of them. So you can use radioactive isotopes in two ways. You can use them in diagnosis, and you can use it in treatment. So diagnosing, you're going to use the smallest amount of radioactive isotope that you can, and you want it to be like very short-lived. So if you have to use any type of radioactive isotope, you want it to break down quickly so that the patient is not going to be continually either exposing others to that radioactive substance or being affected by it themselves. So they call this a tracer. And like I said, smallest dose possible, they want to have one that breaks down quickly. So they have Where is it? Where's, is it in the, maybe it's not in my list. I thought I had it in the list. So in your book, I can show you. I don't know if I have my book with me. I was looking for, I have iodine. Where's my list? Maybe I skipped it. There. All right. So here, when I talk about ones that are either fast or slow breakdown, if you look at this one, zoom. So there are some, nope. There are some that break down really quickly. Those would be more apt to be used there for diagnosis. So see, like fluorine 18, in 110 minutes, half of it breaks down. Iodine 123, 13 hours, half of it is gone. So when they talk about half-life, it's just how long before half of that energy has dissipated. Ones that they're going to use for treatment, they may have to use ones that are found longer, depending on the type of treatment. So these are all ones that are used in medicine. Chromium 51, and if you look at chromium, so chromium is 24, and so in this one, normally 52 is the most common atomic mass. This one's actually a 51, and that makes it less stable. That one's a little different, a little interesting in the numbers. Iron 59, phosphorus 32. Ones that break down quicker are ones that you're going to use more in diagnosis. Ones that break down slower, you might use under conditions of trying to treat. And this is, now I'm going to jump forward, past tracer. If you're going to have external exposure, so if somebody finds out that they have skin cancer, or somebody finds out that they have an organ cancer, so they may use gamma emitters to treat externally, because what do gamma emitters do? Gamma decay goes where? Goes all the way through, okay? So you can either do like regional exposure to a gamma emitter, and that means that everything that you're exposing to is going to be exposed to that ionizing radiation. Cells that grow abnormally fast are more susceptible to ionizing radiation. So the goal is we use this ionizing radiation to damage those rapidly growing cells so that they die, so that we can actually destroy the tumor specifically. So in that one, you look for those. Here's one that they did in a thyroid test. So in this one, they use iodine 123, because I told you it only lasts about 13 hours. So they inject you with a dye of iodine 123. Iodine is only used by your thyroid. So all this iodine goes to the thyroid. And so the thyroid is this little bilobed gland that's in your neck. So this is kind of like its normal sort of look. Kind of looks like that. Okay, like two little glands, there's a little bridge and isthmus that connects it. If your thyroid is irregular in its activity, it will take up this iodine and it will concentrate it in areas that are more active than they should be. And so in this, do you notice how, like this area, okay? The little top of this area up here looks a little questionable, not terrible, a little more uniform, but then look at the bottom one. So this should be the same. So looking at the bottom one, do you see the difference between what would be a relatively normal scan and a scan that shows areas where there's no iodine usage? So in that area, the cells of the thyroid are not using that iodine, so it shows up, they call it a cold spot, which means that there's less than normal amounts. So overactive, having too much in one area, underactive, having not enough, that could show that you have abnormal cells that aren't using iodine, but they're growing there. So there's a mass. So you have a cluster of cells that are not using the iodine, but they're actually like taking up the space of the thyroid. So they're going to use 123 because in 13 hours, half of it's gone, 13 hours, half of it's gone. And so it dissipates really quickly. So over 2 days, there's no more. If they find that they need to treat this, you can do surgery and remove the thyroid, but you could also treat with iodine 131, which has a much longer half-life. You give them a higher dose, and that's considered a therapeutic dose. So therapeutic doses are always more. They tend to hang out or hang around longer, and they're going to have more of an effect. So iodine 131 gets collected, and then it releases ionizing radiation. So it starts to release this radiation, releasing radiation, releasing radiation, to this all the cells that are around the thyroid. And what's that going to do to the thyroid cells over time? Over a couple of weeks, that's going to cause your thyroid cells to die. So that exposure to the ionizing radiation will cause enough damage to them that they die. And now you don't have a thyroid. So now you don't have abnormally growing cells in your thyroid, but you don't have a functioning thyroid. So if you destroy the thyroid, they just give you medication to balance it called Synthroid. So you just take artificial thyroid medication for the rest of your life. But doing this is a means so that you don't have to go in and do surgery. It focuses all of that radiation in that one spot rather than affecting the entire body. And so that's a really useful way of treating. There's another one. So this is when we, with our digital films now. So digital films are really like starting to colorize and give more wow factor in them. So in this, you can see that cold spot, that whole area up here that really should glow uniformly like this one does. So this one would be the normal. A normal thyroid scan, really uniform, a little bit in between, but you can definitely tell that there's something that's not normal about the one that's on the right. They also, other than giving an injection of something that concentrates, they actually can insert radioactive seeds into a tumor. So if a tumor is found, they can do what's called brachytherapy. So they take these seeds and they implant them into the middle of a tumor site. These seeds are typically alpha decay. So that means they're not releasing lots of energy in a lot of different directions. They're only affecting the area right around them. So they damage those cells, damage those cells, damage those cells. Then they can take the seeds out. They can replace them with more seeds if they need to continue treatment, or they can remove it if they find that all of those abnormal cells have been destroyed. This is how they treat prostate cancer. This is also, as someone was telling me about an eye cancer, like in the choroid, that they actually implant radioactive seeds rather than trying to go in and tear it out because of the damage to the retina and the damage to other eye structures. So they actually go all the way in and plant these seeds and then come back, remove any of the damaged area, and sometimes they have to do multiple treatments this way, but eventually this will get rid of all of those abnormally growing cells. Lung cancer is kind of a new interesting one. Lung cancer treatment, so lung cancer is most commonly along the airways themselves. So your lungs are like just a big sponge, okay? So along those airways, problem is with lung cancer, abnormal cells grow really fast when they're exposed to oxygen. And so when they're in the lungs, that's a constant oxygen supply. Every time you breathe, more oxygen's floating by those cells. And so they tend to grow fast. So they're even using nebulizers. So they're taking a radioactive substance, it's in a mist, the person is inhaling it, and it like coats the airways. So any rapidly growing cells in those airways are going to be affected by those radioisotopes. With these, they tend to use ones that are decaying and not releasing a lot of energy in large directions. They tend to use ones that are going to kind of be more localized, alpha decay, some of the weaker beta decays, because that way you're not going to end up with damage to tissues that are in the chest wall, tissues like the heart. So you're not going to end up with damage to that. It's really more specifically helping to focus right on those areas. Problem is, ionizing radiation always targets rapidly growing cells at a higher rate than just regular cells. So when you think about like muscle cells, so muscle cells, once they're formed, they don't regrow, okay? Smooth muscle will, but cardiac and skeletal muscle don't. And so neurons, same thing. So those are, they don't consider those rapidly growing cells. But epithelial cells on surfaces, those grow really fast because you're always rubbing on things, so they're constantly growing back. And so you end up with a negative effect of radiation in areas that are treated. What are some common symptoms that patients have? So they get hair loss, okay? So if they're having whole body treatment, then that can cause damage to the hair follicles. The hair follicles go into their dormant mode, and so the hair falls out. So they can lose hair. They lose weight. So it's because of the GI tract. So your GI tract, like your small intestine, is replaced every 3 to 5 days. Okay, so that means those cells, the lining of that is constantly being reformed because of damage, because of the really rough broccoli that you're swallowing and everything else. And so all of that, as it moves along through, so rapidly growing cells. So that lining can get damaged. And if the lining gets damaged, you can have malabsorption of nutrients, which means that you can't break down and absorb nutrients as well. Oftentimes it causes all of the upset. You either have nausea, you have diarrhea, sometimes you have the both. And that's, again, because it causes damage to that lining and the body's way of trying to get rid of irritation in your GI tract. If it's in your upper GI tract, then you're nauseous. If it's in your lower GI tract, then you're going to cause massive diarrhea. So it's a one or the other. And that's because of that upset, because of that imbalance that occurs. You can sometimes end up with an external rash or even a burn on an area where an external beam. So if they find that there's a tumor that's deep and they want to treat it with external beam, that surface area oftentimes ends up becoming red, rashy. It may look like a burn, like a 1st or 2nd degree burn along with it. And that's, again, epithelial. That's lining type of tissue. So those are much more sensitive to damage. So the last one, yeah, pretty good. Last one, we'll quit there. Last one is the positron emission. They're called PET scans. These have been around for about 50 years. So these are relatively new. So what they do is they use an injection of a radioactive isotope with a really short half-life. So again, this is more for diagnosis. So see, it's fluorine-18. Has a half-life of only 110 minutes. So half of it's gone in 110 minutes. You give a really small amount, as small amount as possible. You just want to be able to detect it. So that fluorine is taken up and it actually gets absorbed and utilized right along with glucose. So it's usually glucose they tag it with, so they like attach the fluorine to a glucose. So that then goes to active cells. One that they like to focus on is really active cells that are otherwise really hard to look at. So the brain, why is the brain hard to X-ray? Because of the skull. Right? So if you took an X-ray, all you would see is the external of the skull. You wouldn't actually be able to see brain tissue. And so having the CT scans, you can see some of the vascular nature, but it's still difficult to look at any kind of activity. It's just there. This is actually, when you have, the more active areas are, the more that fluorine will show up. And so it can actually show active areas within the brain. This has been really helpful when looking at TBIs. What's a TBI? Traumatic brain injuries. So patients that have had injury to the head and they've actually have damage to brain tissue, when you look at it on an X-ray, it just looks like brain tissue. So really you don't know if it's active or if it's not, but a positron emission tomography or a PET scan can help you to see this. So active brain areas, active cells are going to pick up that fluorine-18. Less active areas will utilize it less. This actually really helps them mapping part of the brain too. So they could have a patient doing a certain activity like reading, listening to music, talking, trying to do math problems, and they could actually see different parts of the brain would light up because of this positron, the PET scan. So it shows activity, not just structures, and that was really helpful. To give you an example, here's this one. So this one on the left, here's your normal PET scan. Areas that are red and yellow are active. Areas that are dark are either areas where you have less activity, no activity, or could be ventricles, right? Because you do have some hollow spaces within the brain. So when you look at normal activity, doing the same thing, look at what happens with Alzheimer's. So Alzheimer's, you can see that the activity level is much lower, that there are areas of the brain that are active, like over in this area, active in the normal, but you see how it looks like it's sort of shrinking away. So that's also characteristic of that loss of memory, loss of normal function, normal processes, a lot of the behaviors that people tend to start regressing and becoming less adult, more childlike as time goes on. And that's all because of that brain processing gets slimmer, smaller and smaller and smaller. Okay, so that's really the big thing in chapter 2. Chapter 1 really took a long time because of all of that basic information and stuff that I had to go through. So this is what we'll cover in chapter 2. So you do not have to worry for your test. You do not have to worry about the half-lives. You don't have to worry about the calculation of half-lives and energy remaining and that type of thing. But the other thing that I will